Hey, it's Tish here. Today I'm talking about the derivatives of the Michaelis-Menten equation and how that relates to a catalyzed reaction. So first thing we should note is kind of what's happening in this reaction. We know that we start off with an enzyme and a substrate. When that substrate binds to the active side of the enzyme, we're going to proceed in a forwards reaction and we're going to produce an enzyme substrate complex. This reaction could go both forwards and backwards, and this is the first step of the reaction. The next step, we use this reactant, and we're going to proceed in a forward direction to produce the product. So the difference between these two steps, we can look at the ability of it to go both forward and backwards versus just going forward once we're trying to produce that product. That's because the amount of product that we have early on in this reaction is so minimal, we're not going to have enough of it to actually reverse it. So for now, we're just going to label these as K1, K-1 for that forward reaction, backwards reaction, and then for that second step, forward reaction, K2. So those are going to be our constants. It's just going to be a way for us to kind of assign a quantitative number to the rates of each of these steps. So if we look at an equation, and we kind of apply this, we can say that instantaneous rate of change of those bound enzyme substrate complexes over that rate of change over time. So this is kind of just velocity changes over a certain set amount of time. We can say this is equal to that K1, that rate constant of the first forward reaction, times the reactants that we have. Oh, that's ugly. The reactants. So the reactants are this individual enzyme and the substrate concentrations. We can subtract that by that backwards reaction and the reactant being used in that, which is that bound enzyme substrate, minus the second step in the reaction's rate and the reactant being used. And we can set that equal to 0. So first thing, I guess, when breaking this down, we want to solve for the concentration of E. What we know is we have this equation where we can have the total amount of the enzyme concentration within the reactions equal to those individual unbound enzymes plus the bound enzyme. So that'll account for all of the enzyme in the entire reaction. If we do a little whoop-de-whoop and we rearrange this, we can say that the concentration of enzyme is equal to the total enzyme minus the bound enzyme. So that makes sense. We're going to be able to take this, and we can take this equation, we can plug it in for E. So then we're going to rewrite this really quick. Time is equal to K1, then we're going to say times E total minus ES. We're going to do one of these times that substrate. And then we'll just keep these the same. ES minus K2, ES equal to 0. Okay, so how we solve for this, if we're trying to solve for, first thing actually, we're gonna factor these out. We'll solve for this, we're gonna factor in the substrate, and we're gonna move this around, we'll have it set 0 is equal to the K1 of the enzyme total, that substrate minus K1, we're going to have ES bound times this minus K1, negative K1 of the enzyme minus K2 of the bound enzyme. So now that we can solve for the concentration of E, we can also solve for this. If we factor out the bound enzyme substrate, we can solve for it. And when we factor it out, we want all of that on the same side. So let's see, we'll have this, K1, substrate, K-1 plus K2 equal to K1 over the substrate concentration. So if we want to isolate we're going to divide by this, K1 substrate plus K negative 1 plus K2. We'll divide by this on both sides, and that's going to give us the concentration of that bound is equal to K1 E total times the substrate over K1 times the substrate plus K negative 1 plus K2. So this gives us the equation that we can then plug in both here and here. So the last thing that we need to find, if we know the concentration of the enzymes, the concentration of the bound enzymes, we just need to solve for the product. So in order to solve for the product, we'll kind of just rewrite this equation and show what we already know. If the product, like we said, is going to be that K2 rate, what we're really just looking at is this portion right here. So write this again in the way. The change of the concentration of P over that change over time, which is essentially the same thing as velocity. It's equal to the K2 of that enzyme bound concentration. The Kcat is going to give us our turnover number. And our turnover number tells us how many molecules of that substrate can produce how much product over an amount of time. So essentially velocity. We can say the velocity is equal to Kcat, the same thing as K2, times the enzyme total and the substrate concentration divided by substrate concentration plus Km. So in order to relate this equation to Km, we kind of have to talk about Vmax. So what is Vmax? If we look at the top of this equation and we think about the Kcat, the turnover number, the ability of binding with substrate, with the total amount of all of the enzymes available and the substrate concentration, all of that together is going to give us what we call Vmax. Vmax is when all of the enzymes and the substrates are bound, creating that ES complex, and it's catalyzing that reaction. If we rewrite this equation, we can just say V is equal to Vmax, concentration over concentration plus Km. So Km and Vmax. Now that we can talk about Km a little more, we can say Km is equal to Vmax over 2. Km is equal to half the Vmax. So when half of those enzyme substrates are bound, we get half of Vmax, which is related to the Km. So it's a way for us to tell the affinity, the likelihood, the strength that those substrates want to bind to the Km. If that Km is low, that means that it's not a lot of saturation in the reaction. So it's going to have a high affinity. It's going to want to bind. If the Km is really high, that means there's not too much saturation going on. You're going to have a lower affinity for binding. So that relates to the reaction. And solving for these, you can actually plot these. So if the reaction velocity, that's going to be our y-axis. The x-axis is going to be the substrate concentration. Here we can see time is around 0. So when time is around 0, it's the start of the reaction. We're going to have low substrate concentration. So as that substrate concentration increases, we can see the rate of the reaction, the rate of those bound ES complexes catalyzing the reaction, we can see it's increasing. The Vmax marked here is the point where we have the saturation of all of those bound enzyme substrate complexes. If we look at half of that Vmax, where we're at that half point, half of them are bound, half are full, and we go directly down, that relates to the substrate concentration and the affinity and the Km that we were talking about earlier. So this reaction essentially relates to catalytic activity and how having more substrate is going to cause that rate, the velocity of the reaction to actually increase. That's it. Super easy.